Hi everyone, my name is Colman Madden and I'm an engineer with Google Cloud in New York, focused on the asset management and hedge fund industry. Prior to Google, I spent around 10 years working in the data engineering space. I'm also here with David Lee from BlackRock, whom I've been collaborating with since early 2019. David, over to you.
Thank you, Colman. Hi, my name is David. I work in the financial modeling group at BlackRock. The group consists of a team of engineers, modelers, and researchers working together to develop best-in-class analytics to clients. Today's agenda is as follows. I'll first introduce what we do at BlackRock, then present two use cases of how we generate signals using natural language processing on Google Cloud. First, I'll talk a little bit about how we train against returns to construct a bespoke dictionary to analyze sentiment for single issuers in the structured credit space. Second, I'll talk about knowledge graphs and entity linking, and about how we trained an entity linking model to build a foundation for constructing knowledge graphs. In addition, I'll talk about some use cases for these concepts. Colman will then conclude with forward-looking views of how to conduct investment research on Google Cloud in the future. I lead a team inside FMG called Advanced Data Analytics. Our responsibilities span engineering, financial modeling, and natural language processing. For data engineering, we process data sets that are terabytes in size to extract insight by leveraging big data technologies such as Spark. Some of our work have been previously presented at Spark Summit East. We also leverage managed services provided by public clouds. Our goal is to efficiently deliver data-driven solutions to our clients. As a team, we have a wide range of skills and provide flexible, end-to-end solutions to streamline feature engineering, the building of financial models, and productionization. Our approach to natural language processing is a little bit more focused on research. We pay a lot of attention to recent developments in the applications of text classification, information extraction, and entity linking in the NLP space. The first use case is classifying text in the structured credit market. In the past decade or so, the leveraged loans market size has been increasing. Also, due to private nature of these investments, publicly available structured data sets may be common but sparse. Taking a bottoms-up approach, we analyze credit at the issuer level. We aim to tackle the problem with feature engineering to add more insight to the model, which is to look at issuer defaults and measure a probability of default for an issuer. At the beginning of the year, the US leveraged loans market was around $1.2 trillion. More than half of that is the US collateralized loan obligations market, which is close to $700 billion. In the past 2 years, we've seen record issuances of close to $120 billion per year in 2018 and 2019. This increased market size, coupled with companies assuming more debt, give rise to additional risk in the market. At the same time, risks are becoming increasingly difficult to capture. For example, environmental changes such as COVID had significant impacts to the competitive landscape in multiple sectors, such as retail. As the political landscape and regulatory oversight changes over time, companies are exposed to increased uncertainty. Additionally, they're also held to higher standards. Companies are now facing mounting pressure on environmental, social, and governance. In order to address these issues and capture additional information from alternative datasets, we turn to natural language processing. We analyze large volumes of textual news via NLP to classify text into sentiment scores, as well as other metrics, such as news volume and emotions in these articles. Some of the challenges in predicting issuer probability of default, or PD, over some time horizon are, first, it's typically difficult to find structured data on issuers due to their private nature. In instances of where data is actually available, it can still be subject to sparsity, such as pricing data, due to these instruments lacking in liquidity. Trying to apply NLP to this problem, available news corpora are typically at least terabytes in size and can easily exceed petabytes across multiple periods. Given these, we need both persistence and compute resources to be flexible, whereas they typically are constrained in a fixed computation farm. Thus, we need a flexible environment to iterate and test our ideas so we can extract and classify text for predicting probability of default. Let's take a look at the modeling process here. First, we start off with loading the data. Then we apply transformations such as tokenization, stemming, named entity recognition, and sometimes even applying language models to reason about text in an embedding space. Then we align unstructured text with structured data sets such as returns or spreads. This step has to be done carefully to match market open and close times, as well as time zones, and ways to deduplicate articles that discuss the exact same thing. Once this is done, we query the data stored and train and evaluate our ideas by tuning hyperparameters and finding thresholds to construct an optimal bespoke sentiment dictionary. Then we iteratively roll this dictionary across time for inference. This process has proven to be quite straightforward on Google Cloud. We start off by persisting various stages of our data to cloud storage, which is a highly available distributed store that gives us plenty of scratch areas to test our ideas. Then we provision Dataproc clusters with gcloud in Cloud Console. This provides us with an ephemeral Hadoop Spark compute cluster across our large datasets. An auto-scaling policy and preemptible machines are your best friend when managing these clusters. Recent metrics demonstrate that Spark 3 performance on Kubernetes is catching up to Yarn. This is good news as we can then potentially switch to Spark operators in the future. After that, we leverage BigQuery to run analytical workloads and extract and filter relevant information. BigQuery has similar functions as Hive, storing metadata and being a compute engine. However, for BigQuery, there's no tuning or configuration involved. It automatically handles your workloads and produces results quickly. Finally, we use AI notebooks and cloud storage as a combination to iterate over our training and evaluation cycle. These managed notebooks give us the flexibility to scale our resources up and down through configuration changes. Usually operating on-premise, we need to be very careful about resource consumption as well as capacity planning due to the multi-tenancy nature of our shared compute clusters. Typically, a single ETL job that we've previously done can take up to about an hour, and we have thousands of these jobs to run. On Google Cloud, after carefully configuring our setup, we're able to compact that time per iteration down to 2 hours for the entire dataset. Armed with scalability and flexibility to change the cluster size as well as the type of cluster, we can iterate on multiple tests and focus more of our time on ideation and modeling, as opposed to worrying about whether we're consuming too much compute resources. Some lessons we learned during this exercise. Spark, the de facto open source big data processing tool, is great for ETL and disk I/O intensive jobs. For large-scale optimization calculations, not so much. We turn to distributed compute frameworks such as Dask and Ray for parallelizing these optimization tasks to optimize our runtime or to minimize our runtime. Let's switch gears to our second topic. This one is more exploratory in nature and has received increased attention in the past few years in the research community. We explore the applications of entity linking and knowledge graphs in the equity space. We want to extract information for the correct securities. Moreover, we want to track and identify relationships between entities, so we need entity linking to map text to an entity in some knowledge base. Some examples of applications are extracting and analyzing supply chain impacts to companies' revenues and expenses. Think of Foxconn manufacturing iPhones. Additionally, Samsung is a supplier of screens for Apple. Therefore, understanding correlation of performance between companies due to their shared dependencies in the same suppliers help us better build equity risk models. Similarly, we can analyze corporate structures such as ownership and subsidiaries. And here we define ownership kind of loosely. We analyze this to gain insight how performance of one company affects another. Lastly, we were talking about ESG before. Creating models in measuring corporate governance can be aided with calculating the diversity of boards, experience and expertise of board members, and how a member's track record may affect the company performance that they sit on. On the right-hand side, you can see a snapshot of our partial knowledge graph. It shows the ownership relations of BlackRock as well as Google, and the two companies are connected through Alphabet, which is the parent company of Google, and in which BlackRock owns shares. To construct a knowledge graph, a fundamental step is look at the problem of entity linking, or EL. Here's a simple example. Given a sentence, Larry, whom we know as the chairman and CEO of BlackRock, said at the beginning of the year that BlackRock would place sustainability at the center of investment approach at the firm. In this example, it's relatively easy for humans to understand that Larry refers to Lawrence D. Fink, the CEO of BlackRock, and BlackRock as the investment management company. For a model, the difficulty lies in training a system that can correctly link text spans to entities that live in some knowledge base, such as Wikipedia. The objective of EL is as following. Given a piece of text, recognize, disambiguate, and link entities to an entry defined in some knowledge base. We use BERT as a language model. BERT was developed by Google AI in 2018, and a knowledge base that's a mix of Wikipedia and other sources. In this case, we use Yago. Our task is to detect mentions and disambiguate entities. Looking at this problem, we need to provision resources that can scale with our workload, namely to leverage GPUs for training of large neural networks. The productionization process of these models have typically been complex, and we show how we can use Google Cloud to achieve this. Looking at the following high-level architecture, we can see that connecting BlackRock and Google networks through interconnect and keeping the traffic between the data centers is a good way to start. With a remote interpreter on a virtual machine instance on Compute Engine, we're able to test different types of configurations of GPUs and TPUs and tune them for training. We then stand up a request server to run evaluation on a local machine and then forward the port. Lastly, we deploy our models through TensorFlow serving to expose the entity linking model to clients through an API through cloud endpoints. This end-to-end approach allowed us to quickly iterate and train our models and minimize the deployment time of our models to production. Next, I'll hand it over to Colman to give a forward-looking view of investment research at Google Cloud.
Thanks, David. So David covered two great use cases where his team have been leveraging GCP at BlackRock. And I wanted to talk a little bit more broadly on how the investment industry is partnering with Google Cloud. I don't think it's any secret that the buy side is becoming increasingly dependent on data and AI to power investment decisions. And you'll see that by looking at some of the statistics here on the right-hand side of the slide. At Google Cloud, we believe this aligns really well with our powerful analytics platform and the AI research coming out of Google Brain, which we provide to our customers through our cloud platform. Why don't we start by looking at a typical investment decision flow for a buy-side firm. So firstly, formulate an investment idea, source data to prove out that hypothesis, generate signals from the data, construct a portfolio, backtest the portfolio, present the findings, and determine a capital allocation from an investment committee before moving into production. The blue box highlights the stages of the process we feel are a great fit for Google Cloud. So why run investment research on Google Cloud? Firstly, to provide the ability for investment teams to spin up projects quickly and react to events in the market in an agile fashion. 2, streamline the onboarding of new data sets from commercial data vendors, such as Refinitiv and CME Group, through our data marketplace. 3, burst compute workloads into the cloud and eliminate resource contention from on-prem compute firms. 4, get access to the latest AI research through our APIs and managed services. And 5, orchestrate your ML workflows with state-of-the-art DevOps and MLOps platform. So how do we do all this on Google Cloud? Here's a high-level architecture of how firms are running investment research on GCP. If we start off by looking at the blue box, this is our data acquisition project, where the data engineering teams onboard various data sets, such as market, portfolio, news data, etc. And if we look at the green and yellow boxes below, this is where the research teams are using their tools to access the data sets above. We understand there's often a wall between different investment teams, and we can implement this using our identity and access management tools, while still allowing access to shared resources such as tick history. So let's dive into the GCP products that sit behind these boxes. In the data acquisition project, we can ingest streaming data via our PubSub message queue, or land files on Google Cloud Storage, trigger load jobs into BigQuery, our NoOps data warehouse. Dataflow and Dataproc are available for ETL. We're also seeing a lot of customers moving to an ELT architecture, where they load the data as quickly as possible and then use the power of BigQuery to actually do that transformation using ANSI SQL. The data marketplace allows data publishers, aggregators to to share their datasets with financial firms without the need for any ETL. This is extremely valuable, as datasets are often in the petabytes. You may have seen we just announced BigQuery Omni, which will enable firms to query the data on AWS or Azure from a single interface without any cross-cloud movement or copies of data. We push the compute to the data. In the research projects, quantitative researchers can run simulations on HPC clusters with hundreds of thousands of cores, custom VMs that perfect the ratio of cores to memory. If your workload can handle preemptions and needs to run for less than 24 hours, preemptible VMs allow you to do this at an 80% discount. We just launched confidential VMs, which allow you to encrypt data during processing and even when it's in memory. So moving to the right, our Cloud AI platform allows quantitative researchers to create AI notebooks with the latest TensorFlow, PyTorch, and scikit-learn images on CPUs, GPUs, or TPUs, and pull these data sets straight into Pandas data frames. AutoML allows you to create machine learning models for natural language, structured data translation without having to write any code. These models can be trained to understand terminology that is specific to the financial services industry. Our document AI solutions enable you to process complex financial filings and earnings reports with cutting-edge NLP and transfer learning technologies. AI Pipelines is built on top of Qflow and TFX and provides an MLOps solution to evaluate, train, and deploy machine learning models to production. These models can be shared with other research teams through AI Hub. One really important thing to note here is that this is all deployed by infrastructure as code using something like Deployment Manager or Terraform scripts. So how do you get started? So step one, you want to get the cloud foundations in place. Understand your requirements around networking, security, access management, wrap these up in infrastructure as code, and feed these into your project creation pipeline. Secondly, you want to understand the process for onboarding new data sets and build a data acquisition pipeline to automate this. Thirdly, understand what tools your researchers need and automate the deployment of these tools along with the connectivity they need to access the data required to run their experiments. We want to make life easier for everyone. Thank you for coming along to our talk today. Please add any questions to the dory or feel free to reach out to me or David directly.